welcome back to the second talk, and we have Chris York who will tell us about tautological classes of matrix.
Yeah, thanks for the introduction. So in some sense, this talk can be considered as a continuation of what Federico was talking about. So let me start by just fixing some notation that we had actually from the last talk. So we had some finite set n, one for each hyperplane. And the hyperplanes were specified in a matrix, let's say R by n matrix, full rank. So I have vectors v1, column vector v2, dot dot dot, column vector vn. So there's a full rank matrix, R by n, R being smaller than or equal to n. And usually we'll work over the complex numbers, although any algebraically closed field will work fine. And given this data, Federico introduced, from this linear data, Federico introduced many interesting things to look at. One of them is the combinatorial object that he briefly mentioned as a matroid. And in this talk, I'll just call matroids to be hyperplane arrangement. So we can just use those two words interchangeably, although if you have seen matroids in its pure combinatorial context before, you know that the purely combinatorial notion of matroid is a lot larger, but we won't really be concerned with that for now. So let me fix the notation of M for the matroid of rank R. So I have rank R matrix. And the combinatorial information one keeps is called the bases. What are these? These are a collection of size R subsets, which I'll denote as curly B. So these are size R subsets of N, such that the vectors in that list are linearly independent. And since the matrix that I wrote down has full rank of rank R, those are exactly the linear bases in my set of column vectors. So two such data. In the previous talk, we used notation curly A for the hyperplane arrangement coming from looking at the normal vectors or normal plane for each of these vectors in the columns. So these were the hyperplane arrangement. And by dualizing the picture, we had a linear subspace, which Federico denoted as V. And this was the row span of the matrix A. And this is linear subspace of C to the N. And in Federico's talk, he gave you 2.5-ish models, or nonlinear models, that people have used to study these linear objects called matroids. I'll introduce a few more, just give you a few highlights from the past. But one thing I want you to notice as I kind of survey over these various different geometric models of matroids is that they're somewhat disjoint. So I have some tools specific to one tool, or one geometric model that I can't really easily use on the other, and so forth. And the work I want to present to you today, which called Tautological Classes of Matroids, is a new geometric model for studying these nonlinear objects. And the whole point is that we can now unify essentially all the models that Federico has introduced into a single framework and basically recover almost all the theorems that these models have produced and extend. So this is work with Andrew Berget, Andrew Spink, and Dennis Tseng. With those three. And one of the key driving point for us was trying to study the following object. Actually, let me kind of put it here. a top polynomial, which is a bivariate polynomial in two variables, x and y. Now, if you have seen top polynomials of matroids or graphs before, that's great. If you haven't, that's also fine. Really, the only thing one needs to know for now is that specialization of this bivariate invariant of matroid. So it has two variables, x and y, but if I evaluate one of them at 1 plus a variable and then the other one at 0, this is exactly the characteristic polynomial, or this polynomial obtained by doing this finite field computation that Federico introduced in the previous talk. Well, almost equal. So this one had alternating signs. This one, the way I've written it right now, doesn't have alternating signs, so I'm just ignoring the signs. So let me just say essentially equal, where the left side just ignores all the signs. So what we want is not only log concavity for these characteristic polynomials, but why not some sort of log concavity for the whole top polynomial, which encapsulates much more of the log concavity and unimodality behavior we've seen. So in my mind, all these various different geometric models of matroids kind of fall into two broad camps. And to say what these two broad camps are, let me take a step back and work in a little bit more general setting. So let's set sigma to be a smooth projective fan. What do I mean by that? Take some nice polytope. They look something like this. And then look at its normal fan. So take each of the normal directions of various faces, put them together, so in this example, I get this fan with 5 rays, 5 two-dimensional cones, and one and the origin. So I have a smooth projective fan that looks like the one that I just drew inside RPDM, inside which sits C to the M. Now, given such data, there are two very well-studied combinatorial rings attached to such thing. Some people call one of them the polytope algebra, and the other one the piecewise polynomial algebra. Let me define what these two objects are. So the first one, called the polytope algebra, or often called McMullen's polytope algebra. Let me tell you what it is as a vector space first. So as a vector space, it's generated by these symbols and polytopes whose normal fan coarsens my original fan. So for example, if I had a square, normal fan is a coarsening of my original fan. So if I'm taking the original fan with 5 rays to be sigma, then any kind of symbols on these polytopes that are squares will be a valid element in this polytope algebra. Then I want to impose some relations among these symbols on polytopes. The first one is translation invariance. In other words, if I have two polytopes and they're translates of each other, they're the same. So I want to impose that relation. And another one is often called valuativity. And I'll write that relation here. Valuativity is essentially saying I want some sort of inclusion-exclusion. So what do I mean by that? If I have polytopes PQ in this family, such that their intersection and the union are also polytopes that coarsen my original fan, then this kind of inclusion-exclusion relation should hold. So that's what one means by valuativity. And this is a very well classically studied ring. And now I keep saying ring, although I haven't told you what the multiplication structure is. What's the multiplication structure? Minkowski sum. So I have one polytope, pointwise sum with all the other points in the other polytope. So that's one side of the story. The other side is called a piecewise polynomial ring. And it's essentially what you think it is. So piecewise polynomial in rational coefficients on m many variables. So what do I mean by that? Well, in this case, I'm looking at polynomials in two variables. So for each of these cones, I have a polynomial, and considered as a real function on this fan, they must match wherever the two cones coincide. So for each maximal cone, I have some polynomial. Whenever the cones share a face, the polynomials match up. Hence the word piecewise polynomial. And often one works with modding this out by global polynomials. So if I have the same polynomial over all the different cones, so it's genuinely a polynomial function on the entire thing, I mod out by the ideal generated by that. Now, if you're geometrically inclined, you might recognize this left-hand ring as the growth and decay ring of vector bundles on the associated toric variety. Not too important to know that. And also on the right-hand side, geometers might call this the cohomology ring of the associated toric variety to the fan sigma. So in geometric context, both of these are very well studied, and also in combinatorial context. And really the key kind of objects one studies is that there are two distinguished maps from each of these rings called the Euler characteristic map, which I'll denote as chi, and the degree map, denoted as degree, to the integers. Now let me tell you what these maps are in terms of what happens when I have a polytope. So let's say I have a polytope P. The defining characteristic of this chi map, the Euler characteristic map, is that it counts the number of lattice points. That's the characterizing property of this left-hand side map down to Z. Now, if I have a polytope whose normal fan coarsens my original fan, I can consider an element, often denoted as HP. This is a piecewise linear function defined as follows. Its value on X is the maximum among all points in my polytope as I consider all the different pairings. So I have some point, and I look at what the maximal pairing with anything in my polytope is, and this becomes, my polytope being defined by finitely many half spaces. This is a piecewise linear function that is attached to a given polytope P. And this degree map, the characterizing property, is that when I take the support function, take it to the top power, this exactly outputs the volume of my polytope P. And if you're someone who likes polytopes, both of these quantities, the lattice point counting and volumes, are quite ubiquitous in study. Now one might ask, okay, how are these two pictures related? And there is a classical picture that relates these two. So I want some sort of a commutative diagram such that the whole thing commutes like this. And let me say how this commutativity comes about. So first, there's an isomorphism, in fact, between these two rings called the exponential map. And it's literally taking the exponential. So let me define it on the generators once again. So if I have a symbol P on a polytope P, this exponential map sends it to exponentiating this support function. And of course, you might be a little bit worried, like, oh, the right-hand side is an infinite sum. It's an exponential function in HP. But when you modify the global polynomials, anything above degree m piecewise polynomials actually gets killed. So this is well defined as is. And I might want that, okay, if I start here, apply the exponential map, and then apply the degree map, maybe that's the same as just applying the Euler characteristic map. Well, that expectation is a little too naive. But the way to correct this is through what's called a Taut class. So there's some element called a Taut class in the piecewise polynomial ring, which I won't define. And the point is that this whole diagram commutes now with that correction. So if I start with something on the left top, apply the exponential map, multiply that thing with the Taut class, apply the degree, same thing as taking the Euler characteristic map. And the fact that this diagram commutes now is the classical Hertzberg-Riemann-Roch theorem. But for many combinatorial purposes, you don't want to compute the Taut class. Like, this is almost impossible to compute as soon as like the dimension hits 9 or 10. Or in fact, there are, and probably there will be still several papers just studying the properties of Taut classes of various different fans. So one point I want to make today is that for a special case in the context of matroids, there's a replacement for this Hertzberg-Riemann-Roch that's quite non-standard. And it does some miraculous jobs in unifying many things and explaining and giving us some new theorems. Let's specialize this picture back to the context of matroids now. So my fan sigma will be what's called the permutohedral fan, which I denote as A sub n minus 1. What is this fan? Probably the quickest way to say it, and the most relevant in our case, is that it's the normal fan of the following Minkowski sum of various polytopes. So we'll get all pairs of indices, and then convex whole of the two corresponding standard basis vectors, and then take Minkowski sum. So for instance, when n equals 3, what is this saying? Look at all the edges in my standard simplex, like this one. Look at all the edges and take Minkowski sum. So if I take Minkowski sum of all the edges in this, well, first let's take Minkowski sum of these two. I get something like that, and then add this. So this will be the polytope, and then I take the normal fan of such thing. So this is the permutohedral fan, and on this fan, I can consider these two different rings, which I know is isomorphic, but has or see some different combinatorial properties. Matroids and the various models that one uses to study matroids come in two different flavors according to different rings. So the first one is called a base polytope of a matroid. So this is a model that Federico did not mention in his talk, but it's very well studied. So what's this polytope? So given a matroid M, this base polytope is the convex whole of the indicator vectors for each basis. So I have a bunch of these subsets of size R. For each of them, I have the indicator vectors. Take convex whole. And the key property of these base polytopes is that they coarsen the permutohedral fan. In other words, it makes sense to talk about this element P of M in my polytope algebra of the permutohedral fan. Now there are many theorems that one can say about matroids going through base polytope as its geometric model. But let me mention just one of them due to kind of time constraint. So this is Cameron and Spink from 2018. And what's the statement? The statement is as follows. Let's try to do some lattice point counting of the following object. Take the base polytope. Minkowski sum that with some multiple of the standard simplex. So by triangle, let me just denote the standard simplex in Rn. And then some dilate of the opposite standard simplex. So convex hull of the negative standard vectors. And the content of their theorem is that this is essentially equal to, I say essentially because you have to do a little bit of change of variables and linear transformations. But basically, when I do this lattice point counting over various dilates of standard simplex and its opposite, you exactly get the top polynomial back. So this is one instance where one can see the top polynomial in a more geometric setting. So that's one story. What about another one? And this is one that Federico did mention in his talk, where he at least said the word Bergman fan and wrote this notation sigma sub m. It's a subfan of my permutohedral fan. And I won't define what it is, but the key property is that this subfan gives a class, which I'll denote as delta sub m, inside the piecewise polynomial ring. Now, if you're cohomologically inclined, Federico mentioned that there's this variety called a wonderful variety, and I think he denoted this as take the vector space, the row span, get rid of the hyperplane, so I'm looking at the arrangement complement, look at some map, and take closure. It's some subvariety and some bigger thing. So as a subvariety, in fact, it's smooth. So as a submanifold in some bigger thing, it has a fundamental class. So you can look at its homology class, and that homology class exactly is this delta that I'm calling delta of m. So if you like to think of this as genuinely the cohomology ring of the associated toric variety, piecewise polynomial, then that's the geometric idea. And let me just restate the theorem that Federico mentioned due to Junha and Eric Katz in the following way. So this is the theorem where he talked about how to get the coefficients of the characteristic polynomial back. In this language, the statement is that when I multiply this something in my piecewise polynomial ring times the support function of the standard simplex times support function of the opposite simplex to some power. And I can vary I as I would like. The content is that this exactly equals the ith coefficient of chi m of q over q minus 1. So exactly the coefficients that we wanted to show law concavity for in the previous talk. And this is essentially one restatement of such thing. Now, one thing that kind of puzzled me when I first looked at these theorems, you look at this, And then you look at this. Matroid, standard simplex, opposite simplex. Matroid, standard simplex, opposite simplex. Top polynomial, some specialization of the top polynomial. How are they related? And I asked essentially all the authors, didn't know. It was quite mysterious how they are actually related. I mean, like, the better question is, like, how can they not be related? Like, they must be related in some way. And there are many, many other kind of formulas that express the top polynomial or the variant of the characteristic polynomial in these kind of geometric ways. And they all seem to have some thematic similarity to it, but it was quite unclear how to relate any of them. So in the last remaining 15 or so minutes, let me tell you the model that we built that basically outputs all these geometric formulas in one go. Any questions at this point? So here is the key definition. And the thought is as follows. The data I'm given is a linear subspace. How can I make some interesting nonlinear thing out of a linear space? Well, if I just use the linear space, I'm not going to get anything new. But maybe I can create some interesting vector bundle, all of whose fibers look like my original linear space. So that's the key idea. So if I can create some sort of vector bundle, I mean, I'm given a linear subspace. Can I create some vector bundle from that linear subspace? So here is the statement. So let's say, once again, I have a linear subspace V inside C to the n, which was the row space of this matrix A, corresponding to my matrix M. I'll define what the vector bundle is, but I'll also tell you a purely combinatorial definition also. But this is where the geometric intuition comes from. So let's define vector bundles called S, V, and Q of V. And what are these vector bundles? These are vector bundles on the toric variety defined by the permutohedral fan. But really the only thing we need to know is that this toric variety has as an open subset this projectivized torus. In other words, take the standard torus, so C star to the n, and then projectivize. So it has some big open part consisting of a torus. And let me now finally define what these two vector bundles are, SV and QV. So what's S of V? I'm going to specify for you what the fiber over a point, let's say T bar, in this projective space, or projectivized torus is. So I'm specifying what the fiber of this vector bundle is on an open subset. And of course you might have to worry, does it extend to the whole thing? But let's sweep that under the rug for now. But this gives you the key property that I want, which is that the fiber of this vector bundle, which is going to be a vector space over a point in the torus, should be exactly applying the action of the torus onto the vector space. So I have a point T in the projectivized torus. So let's say T equals T1 dot dot Tn. And because it's in the projectivized torus, that's what the bar is for. But take any lift, so T1 through Tn. And then what do I mean by acting on the vector space by T? Scale the first coordinate by T1, second coordinate by T2, and so forth. So I'm using the torus action to just move my vector space around as I change the base point. And for technical reason, I actually act by the inverse. But that's more of the technical issue. So this we call the tautological.
Is multiplication morally the same as the multiplication sum that we just talked about?
It's very related, actually. Yeah. If I have time, I'll get to it. And basically the same thing for Q, where the fiber over the torus point is the quotient by the same vector space. So I mean, essentially S and Q have the same information, but it's sometimes useful to use one over the other. So this we call the tautological subbundle, tautological quotient bundle. I mean, if I'm given a linear space with some nice torus action, it's like the first thing one would try to do if I wanted to build a vector bundle from it. Now I promised you a purely combinatorial definition. So once one has some geometric idea, one can translate everything that's going on in here into the following purely combinatorial context. And the tools behind it is somewhat standard. So I'll just tell you what the final answer is. To define it, let me define one more thing, which is a series of matroids called M sub I, built from my original matroid M. So first, let's make these new matroids, M sub I, for every I ranging from 0 to n, where the bases are now going to be subsets of my ground set n, such that its size should be I, and big I is either contained in or contains a basis of n. So given an initial data of a matroid, I can make a whole sequence of matroids where I declare the bases to be exactly as stated. Then, what one can note is that I can define two elements, S and Q, and both of these are going to live inside the polytope algebra of my permutohedral fan. Let me define the S one. It's the sum as I ranges from 1 to R of the symbol on the basis polytope of mi minus 1 over the polytope of the ith matroid that I've built. And of course, one should always worry, like, wait, can I actually divide in this ring? And turns out in this case, in the polytope algebra, these generators coming from the polytopes, they are actually invertible. So this symbol that I've written down actually makes sense, and one can take this gigantic sum. And one does similarly, where this now goes from r plus 1 to n, same thing. So this is the purely combinatorial object that lives in the polytope algebra side, but it comes from this geometric intuition of thinking about what can I do to build some sort of vector bundle. Now, given a vector bundle, one of the first things one studies is its Chern classes. Let me give you the purely combinatorial definition. So the ith Chern class of, let's say, this S element in my polytope algebra, this is the ith elementary symmetric function of, let's say, h1 dot 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 hr, where here by hi, I mean the difference between the support function of the I minus 1th matroid and then the base polytope of the ith matroid. So So I'm taking consecutive differences of these matroids in my list, looking at their by looking at their support functions. So these Chern classes now live in the piecewise polynomial ring. Okay, so I built all these things. What are they useful for? So let me finally tell you the theorems about these objects. So the theorem is in 4 parts. The first one is almost an observation, but an important one. So if I take the first Chern class of Q, let's say, this exactly returns for me the support function of my matrix polytope. I mean, given this kind of definition, and the definition given here, I'm just saying, like, take the telescoping sum, and then you get the support function of the original matrix polytope back. So it's like almost a trivial observation in that sense, once one has done this work, but it's a good starting point. So this is the first Chern class one can consider. What about the top one? So this vector bundle, Qm, being a quotient of n-dimensional space by an r-dimensional subspace, its rank is n minus r, so the top Chern class lives in the n minus rth degree. This exactly is the class associated to the Bergman class. So just by considering the first and the top Chern class of these vector bundles, I'm interpolating between the 2 models, the base polytope and the Bergman class that we saw. So that's the good news. Now, if I wanted to think about what Federico called the conormal fan is, basically what one does is, let's see, I take this QL, or the Q bundle, and then restrict it to the wonderful variety, and then look at its total space, or projectivize total space. So I have some wonderful variety, I have a vector bundle, projectivize each of the fiber. In Chern class language, this basically is equal to considering Chern class of M with some Chern class, I won't specify what, of the S. So let me spare you the details, but the conormal fan story also naturally arises by using these vector bundles. And Lauren asked, is this twisting related to, or this twisting related to this addition or multiplication map that Federico introduced? And the answer is yes, exactly. And in fact, this is the conormal space. This is the critical set variety, in fact. It's exactly that. And the twisting is built in by construction. So when one unravels what this really means, one exactly gets the critical variety back. Okay, so these are mostly observations once one has built this vector bundle. What are some things that now one can prove? Well, I want to compute every single possible degree numbers. So take standard simplex to some power, opposite standard simplex, or the support function of that to some power, some Chern class of the S bundle, some Chern class of the Q bundle. As I, j, k, l varies freely, I want to consider all these degrees and keep track of them in a polynomial with 4 variables. And if you're bothered by the minus z here, it's just to make the coefficients all non-negative. Okay, so I'm keeping track of all these numbers by a polynomial. Turns out this exactly is the top polynomial in the following sense. So it's a 4-variable transformation where there's a part that does not depend on the matroid but only on its rank. So it's this part. And then there's the top polynomial part. And that's it. Like I wanted to compute this, and when one does it, it comes out to be the top polynomial. And needless to say, the computation one does for this doesn't depend on any of the previous geometric computations that people have done before. The way we do this is we write this down, we pray that we can compute it, and then when we go on to really compute how these Chern classes behave like, turns out they actually have this nice deletion contraction property. And after one uses that, this just falls out. So it's, I would say, elementary but a long computation. What's the third theorem? This 4-variable transformation of the top polynomial, the one that I've written down here. This polynomial has log concave sequence, simplex of coefficients. And the true thing to say for those who might know these words is that it's a denormalized Lorentzian polynomial. But what does this mean? I have a homogeneous polynomial in 4 variables. I can plot each of the coefficients in a 3-dimensional simplex according to the different monomials. So I have degree homogeneous polynomial in 4. I plot these coefficients. Now read in any EI minus EJ direction. All those numbers form a log concave sequence. In fact, it's a little bit stronger, but this is probably one of the easiest.
Did you say Lorentzian?
This is denormalized Lorentzian. Take the Lorentzian polynomial, denormalize it, and this will be exactly that. And the last theorem is the promised replacement of the Hertzberg-Riemann rock. So there is an isomorphism from the polytope algebra of the permutohedral fan to the piecewise polynomial fan. And let me draw this diagram again. So it looks almost exactly like the Hertzberg-Riemann rock, but with one exception. So first, this map is no longer the exponential map. We named it zeta, but we have no good reason. Like, if you want to use different symbol, totally fine. There's this weird exceptional isomorphism such that this diagram commutes without using the top class, but the powers of the standard simplex support functions. So I had to kind of squeeze that in there. But yeah, take the sum of powers of the support function of the standard simplex. That essentially replaces the original top class. So this thing is very computable, and one can actually work with this version of Riemann rock. Alex Spink suggested we call it the Riemann-Mach theorem. I don't know if I really like that, but yeah, we have some replacement. So in the last remaining minute or so, let me just mention some corollaries. So the first one is that one can recover essentially almost every geometric incarnations of the top polynomial or the characteristic polynomial that I know of. So I mentioned Hug-Katz, also mentioned by Federico in the previous talk. I mentioned one by Cameron Fink of the lattice point counting. There's also one due to Fink and Spire coming from some sort of Fourier-Mukai transform. There's also one due to Lucio Di Matrano, Felipe Rincon, and Kristen Shaw on CSM classes, which are actually critical in the computation that Federico mentioned in his work. All of these, basically, like for the first one, apply 2 with the second fact. For Cameron Fink, apply this bridge between polytope algebra and piecewise polynomial with number 2. This falls out. Basically, combine 1, 2, and 4 appropriately, and we get all these formulas back. And there's like 2 more, but I won't really mention. And this extends all known log concavity. So Federico mentioned two, one for the characteristic polynomial, and the one where I've shifted it by plugging in q minus 1 instead. All of those log concavities stored in this one statement, number 3, and more, of course. And lastly, some other conjectures concern these flag matroids, and there was also a conjecture about this G polynomial of Spire and so forth. Basically, just use these 4 ingredients in an appropriate way, they all fall out pretty easily from that. So this is the model that we built, and it unifies many of the geometric models that have been used to study matrices before, and recovers many of the theorems and extends them and generalizes them in a pretty easy way with this framework. There are still many questions open, actually, about these vector bundles. And I'd be happy to tell you more about what's been developing since then, including even a type B story of this whole thing. So this vector bundle story turns out to be the right kind of flexible object one can use to maneuver to get or branch from just the classical matroid case to various other kind of stories. I'll stop there.
So you know my question that's coming, right? So some of us like linear spaces of symmetric matrices. So Cn is the space of symmetric matrices, V is a linear space, T inverse is the inverse of a symmetric matrix, and the permutohedral variety is the space of complete quadrics. Can you do that?
I hope so. I haven't tried. But it has a nice group structure. What's unclear is to what extent this localization theorems that we use for torus localization holds. But if that hurdle can be overcome, which I haven't really checked, then the rest should be fairly easy. Yeah. But if there's a difficulty, that will be the step. Yeah. And then, all right.
Yes, sir. Here was a question.
I have a question. So, in the original picture that you drew for the Herzberg-Friedman-Rock theorem, you showed that if you evaluate the degree map on the top power, you get the volume of the polytope.
Mm-hmm.
But then later you modified it by multiplying by the Taut class. Is there any way that the volume of the polytope computation is preserved in this story, or does that get thrown out by modifying the map by multiplying by things?
So the modification is, what the modification is doing is going from volume computation to the lattice point computation.
Okay, sure.
So in that story, like the lattice point counting, of course, the error polynomial, for instance, has more information than the volume. So it will, and the fact that that has more information requires, in some sense, that top class to be there.
Yeah.
Yeah. So you can use 4, for instance, to compute error polynomials of any polytopes that coarsen, whose normal fan coarsens the permutation, and this recovers the result of Postnikov, for example. Yeah. Yeah.
So you said that map, that isomorphism zeta is very special. So
It's weird.
how can you help us understand what magic allows it to happen, or?
So the magic, okay, so at the end of the day, the magic is this, which is if some polynomial or Laurent polynomial is 0 mod 1 minus ti over tj, that's equivalent to saying it's 0 mod ti minus tj. I mean, I'm like, it feels like I'm saying something trivial, which it is like trivial, but the ti minus tj for different fans will have more than one term, or more than 2 terms. So what I'm writing here, this I'm thinking of as ei minus ej, but then take like exponential up. Like that's the sort of picture I'm having. But if the edge directions are more complicated, things like this won't really work out. And there are characterizations of these two rings in terms of Laurent polynomials or polynomials with some compatibility condition coming exactly like this. So the key property at the end of the day comes down to like this like elementary like thing. What is the geometric meaning of this zeta map? Let me just take 1 minute to say what it is. It's characterized by sending the structure sheaf of the wonderful compactification to the cohomology class of the wonderful compactification. But now defined in that way, it's not even clear if it's a well-defined map or if it's even a ring map. But it's a consequence that we know it exists, that must be a characterizing property. But I don't understand this map better than this. It's a mysterious map. Like, I would like to understand it more.
Just trying to relate this to Federico's talk. So Federico's
Sure.
talk, the orthogonal complement of B plays an important role. Is that somehow in your second vector bundle?
That's right. Yeah, so I have this quotient. So if one didn't want to like fix an inner product, then taking duality would be taking the quotient. And that's where if I'm looking at the vector bundle where each of the fiber looks like this, then on the base I have the original matroid, and the fibers look like the orthogonal space. So that's where the idea comes from.